Hello, my name is Ingo Blechschmidt. I'm one of the keynote speakers for the workshop on categories and logic organized by Peter Arndt as part of the World Congress in School on Universal Logic. And I'll report about exploring the internal language of toposes.
But what exactly is a topos?
Excellent question, Anna. So a topos is a kind of category, E. And you already know an example for topos. For instance, the category of sets is a topos. The special thing about toposes is they all have a so-called internal language, which we can use to do mathematics in. So for instance, if we write this, where phi is a statement, then this actually is just the same as saying that phi holds. But there are also various different toposes, and for those, the internal language is quite interesting. For instance, we also have the so-called effective topos. And just to do one example, if we say inside the effective topos that for any natural number n, there's a number p such that p is larger than n and such p is prime, then this does not mean that for any number n there is a prime larger than it, but then this means that there's a Turing machine which, given a number n, calculates a prime number p larger than n. So this statement is true in the standard topos set and also in the effective topos.
You said something about Turing machines. What about the statement that any Turing machine holds or doesn't hold?
Any Turing machine holds or doesn't hold. So this is a statement which trivially holds in the standard topos, at least if you adopt classical method logic. But this is a statement which does not hold in the effective topos, because there it would mean that there's a machine which, given a Turing machine, decides whether it holds or doesn't hold. And it's well known that such a halting oracle can't exist. So that's the difference between these two toposes.
And I read in your abstract that your research is connected to algebra. And where is this connection?
Yeah, it's as follows. So start with a commutative ring. Then you have a certain topos associated with that ring, namely the topos of set-valued sheaves on the spectrum of A. And this topos contains a mirror image of A called OA, which from the internal point of view of that topos will just be a plain old ordinary ring. And the cool thing about this mirror image is as follows. So firstly, A and OA are very much related. For instance, A is a reduced ring, which means that it doesn't have any nilpotence if and only if OA is reduced. So this shows that this is not like some arbitrary new object, but that it has a relation to the ring. But then there are also statements which are unique to OA. And one of the most important of those is the following. Any element which is not invertible is nilpotent. So this is almost a field condition, which would say that any element which is not invertible is zero. And so this allows us to import a huge corpus about fields or almost fields and to apply that corpus to OA, even though A is not a field and its dogs are not fields. So this is a way of using the internal language of toposes in algebra. And in my talk, I'll report on similar things, firstly this, and also on algebraic geometry, and I'll try to be as understandable as possible.
Cool. Finally, I can use my algebra knowledge in real life. So I see you at the conference.
Thank you very much. I'm very much looking forward to that.